and I suppose we're all tired. So I don't know what I'm going to do. Perhaps we can take 20 minutes or something like that instead of a full hour, I suggest, for a small discussion about today. If anybody has suggestions, are welcome. I have thought at one possibility, which is the following. There were a lot of topics today. There were a lot of different presentations of different kinds, historical theoretical observations. I have picked up from the discussion 3 points of disagreement, or apparent disagreement, which I would like to bring back to you very rapidly and get either a confirmation of agreement or an agreement or a opposite point of view, or even in something, a few topics. So let me say which one were the interesting points that I picked up. So 3. The first one, in the first 2 presentations, I skipped the historical one. I know Lemaitre wonderful, but I don't think there were much to deal with on it. Is the following: I heard, which I didn't know, that if the lambda CDM model seems increasingly extraordinarily well supported by all observations, which means that current fundamental physics plus mysterious dark matter seem to work very, very well. Nevertheless, there is a tension in the data, which somebody seems to say more yes, somebody seems to say less yes, between the value of the Hubble constants, if I got it right, theoreticians were aware of that, measured either sort of low redshift versus high redshift, or in terms of direct measurement versus within the full model. So the question is that, is there this tension? Is that credible? How likely is it to go back to us as theoreticians? Should we take it seriously? Is that a red flag that the observers are saying, aha, here there is something new interesting? Is there a comment about that? You seem to have some, when this was said, you seem to have some...
Oh, well, I mean, there is a question of personal judgment. I mean, about how strong, I mean, there is a tension with the current interpretation of the data, of the teams, and so on. No obvious systematics were found. And so if you look at direct measurements versus others, and that doesn't have to be high redshift, because that's what we all have talked about. I mean, it's really direct measurement versus others. We may have something to understand, and that might be not that easy. And Nicole, I think, pointed out, I mean, you have to, that depends on which model you are putting in. Well, direct is direct. So the question is, are there any, do we really understand, and that there are no systematics of substantial left, in particular in direct measurement? Who knows? I would say this is too early. We have, well, it's not quite 3 sigma.
What I was trying to say this morning is there is this coincidence. If you look to the model-dependent analysis, you are on the low side. If you go to the direct measurement, you are on the high side. That, to me, doesn't mean anything apart from the fact that there is this difference, okay, at the moment. Now, there is a difference, and the question is, if you are consistent with different data sets under the assumption of a given theoretical model, that theoretical model should more or less be okay. This is the balance at the end, okay? But if on the other side, I mean, there is an evidence that H0 is on the higher side, 73, 72, 74, that creates a problem. So it must be taken into account. But as I mean, it's a matter of understanding what we can do. What I think that the next step should be is to try to move towards a model independent analysis, which has started to be done, which is weak in the sense that there are some assumptions to be taken also in that approach. But that may be probably a more promising way of testing these tensions.
So the evaluation of the equation is CDM.
So I think this is a real opportunity, and I'll emphasize this tomorrow. I think nobody thinks lambda CDM is a satisfactory theory. So it's a satisfactory model, but not a satisfactory theory. So we're looking to either break it or figure out what its fundamentals are. And H0 appears to be a portal right now to either break it or make a discovery, because you measure H0 directly and you get one value. You measure it indirectly, assuming that lambda CDM is right, and you get a value that disagrees by 3 sigma. And it could be that the systematic errors will resolve it. There are systematic errors on both sides. But it could be that both numbers are right and that lambda CDM is wrong.
Could you just say why is that nobody thinks that this is a satisfactory theory? This is a strong statement.
Well, because it has three. I mean, I'll give my talk now. But,
oh no!
So it has three. It has three pillars. It assumes inflation. We don't know what the physics of inflation is.
Okay.
It assumes that the dark energy is quantum vacuum energy, and the best.
It assumes what?
Or lambda, which would be, in my mind, even worse. And then it assumes that there is dark matter particles that move slowly that we haven't discovered.
Oh, we don't know.
So, I mean, it's a fantastic intellectual achievement, because with 6 numbers, you fit the entire universe. And in the United States, it takes 10 numbers to do the phones throughout the country. So 6 numbers to do the universe is pretty damn good. But it's not a fundamental theory.
I guess one way to formulate this is that, it's a great effective theory, and the question is, do we have found really an observation that really shows that it actually fails even as an effective theory? And that's why this is so important to know whether this is a systematic effect or not.
But Michael's point was even stronger with that, because he's saying that in spite of the difference between H0, lambda itself, lambda CDM itself is not a theory, because there are 3 weak points, right? Inflation, I don't know.
But I think that's not controversial. I think we aspire to something better than lambda CDM.
Some aspect of this are
Yes.
controversial.
Yeah.
No, but I thought
Some
that
aspect of this are controversial. But I mean, everybody would say agree that this is still like our control. And I think there's agreement that inflation is not something we understand. It's the missing part of the story at the very least. About lambda, I think there.
But I mean, it's kind of another example in physics would be the Rydell-Ginzburg theory of superconductivity. So that was a good model. That was a good, let's call it model. But BCS is much more satisfying. It's a fundamental theory.
But some dangerously close to what I've been hearing for decades, which is the standard model is part of the physics, the other standard model. It certainly is so non-satisfactory, and we are just seeing some little discrepancy. It's 30 years to be here, so it has come out right, and there's really 3 sigma discrepancies on all the one after the other one. It doesn't have to be the same story, but it's starting remarkably interesting. And that is saying yes to the head.
Yes.
You had a comment.
Yes. So, okay, for Denmark, let's do it tomorrow. But today, I would like to talk with Francois, because I met many people in the bank collaboration, and all of them, they told me that this discrepancy is true, and it is bringing a portal for new physics. So there are not just one, many. So I thought that you are telling contrary. You say that it will disappear.
No.
No, okay, you agree.
Absolutely not. That's not what I've been saying publicly many times. I think that, if in 20 years, the direct measurement, they have been redone many ways, and there is studio type, which is, it's all confirmed. Well, yes, we've killed, this effective theory, and it's not even an effective theory that works. So, I completely agree with that. Now, I've been saying that, well, the direct measurement is a very complicated one. Okay? Nobody has played with the data because it's not even public, the recent one. Okay? When it was done once, the previous days, George actually found that the way the outliers were dealt with were not very satisfactory. It's not even possible now because the newer risk analysis is not even public. So I'm just saying, well, yes, it's tremendously important. So if this is confirmed and we don't find some new elements and just say, well, and there's been, I'm old enough now, we've been looking at this on data and the interpretation. So many things that were supposed to kill that version of the theory. Okay, well, many times we found that, well, the data was just wrong, or at least the interpretation of it.
And I also got a sort of wrong impression, but we could clarify. That was very useful.
I'd like to, can I just point out that we're talking about a 0.2 magnitude error. So you're telling us there's a 0.2 magnitude error between these two that is somehow in the systematics. And I frankly don't understand where that error is. And you're saying it's there, which is nice to say, but it's not as, I completely agree that people have to publish their data. There's no excuse when you publish a paper of this sort and measure the whole problem, you don't publish the data at the same time. I completely agree with that. But 0.2 magnitude error is difficult to come up with in this.
I completely agree with that, and I could also say the other side of the flip side of the coin. For instance, we have been cutting the climate data in many different sub-pieces, and they all agree and giving the same thing. So yes, there can be what we call the common mode. Okay? Of course, this common mode hasn't been invented by anyone yet. So I'm being pretty low-key on this. But in terms of cross-checks, of number of things that say the same answer in independent subsets, that's where we are. So we haven't identified, and nobody yet has identified, maybe it's going to come.
Yes.
But how about the low multiple L equals 20 power of this optimal alignment, those things? Do we really understand this? I don't think so.
Well, you are asking several questions there.
Suppose we really agree on the situation.
Well, so I'll tell you what I think about that.
Okay.
Let me go to the second point.
Can I just mention one thing? The REIS data will be available, okay? But just back to your point about George's analysis, in the end, his number was only a little bit smaller than REIS 11, with a slightly bigger error bar. And to some degree, it depends on how you treat different outliers and all that. But in the end, despite all of George's bravado about how we're wrong, his number was hardly different from ours. So, I think it's and now there's the holy cow result that, gives us about the same number. I think there's definitely room to consider the possibility that we might be onto a real difference between the direct measurements and the CMB model. Maybe there's nothing there. Maybe one or both teams are wrong, but I think there might be something there.
Thank you. Let's go to question 2, which is a strong disagreement. This might be shorter, and I want to understand if the disagreement is there or is not there. So we heard first from Astrid and then from Alessia about the asymptotic safety and the program and the beautiful program. But there was a very strong objection idea. So I want to understand when it's there, it's not there. The objection being, and if I got it right, that it's not possible to have at the same time a 2-point function which is soft at the instrument of Violet, which is sort of the main point of this approach. and the standard analytic behavior of two-point functions.
Right, you do, yeah.
So what is exactly the point? Because I mean, it was cut with a strong cross-body estimate.
Right, I mean, in quantum field theory, Green's functions, they have to satisfy certain analyticity properties, right? Now, they have to satisfy these properties if you want causality and so on. Now, then, if they satisfy these properties, then necessarily Green's function must have either pole or branch cut somewhere on the complex spectrum. Okay, this is one fact. I'm not going to basic and revision it. This is like basics of quantum field theory. Then there is a second part. And now if you take this two-point function between spin 2, spin 2, okay, then you can prove very easily by using spectral representation, Shell and Lemon, that if you make this gravity weak in ultraviolet, such a Green's function necessarily would have either branch cut or a pole with a complex residue. Which means that this theory, taken as a quantum field theory, propagates negative norm states or complex norm states, both, basically. This is just a fact. It would be impossible to dispute. So then I had a question simply, there must be some assumption that they are making, relaxing some of these analyticity properties in that theory. That was my question.
Yes, I think maybe one of the points would be sort of a number of assumptions that go into the theory might not necessarily hold in this case. For instance, the question whether it's really adequate to analyze the graviton propagator around a flat background in this case. So maybe the correct way would be to do it around a self-consistent background, which would necessarily be curved because the cosmological constant isn't zero over the and then this might change some of the properties, but I think the point that you're raising is
then this means that you don't have theory on Minkowski background. Then you should say at the beginning that you have a theory but doesn't have Minkowski as a background. Sorry, this is a huge statement now.
No, so the self-consistent background, the one that you really should be looking about in order to decide whether the vacuum is stable or decays, that would be one that should be a curved background. That would be the correct solution to the equations of motion in the presence of the cosmological constant. So that Minkowski background is unstable isn't necessarily a physical problem because the physical background doesn't.
No, it's a problem because this means that this theory you cannot define on Minkowski. This is a huge disadvantage compared to Einstein gravity. Einstein gravity can be defined on Minkowski, no problem, right?
Well, but I mean, physically we care about the definition of quantum gravity around a physically realized background.
But we do almost in Minkowski space.
Just float them.
No, that will not help. No, you see, that will not help you. You should have. So you see, there is no free lunch in this kind of business, right? So if you want to, no, because quantum field theory was created during decades, right? We cannot just change it overnight because.
Yeah, would you be unhappy if a theory was consistent in the present cosmological constants around the system and would be inconsistent around Minkowski?
No, it would. So it's not about my happiness. So, for example, there could be a statement that there do exist some class of theories which cannot be defined on Minkowski backgrounds, but can be self-consistently defined on some de Sitter background, let's say. Okay, and those theories defined on de Sitter background are asymptotically free, okay, or asymptotically safe. Even that is very suspicious, and I can tell you why. Because background is an infrared property. Okay. When you put background with a curvature which is below your cutoff, this means that for high momentum modes, this background is not visible. It's like exactly the same thing. When we do experiments at LHC, we assume that we live in Minkowski space. We are taking into account dark energy, right? Because high momentum modes, they see themselves as if they are in Minkowski space, unless you put curvature which is comparable to your cutoff. Now, okay, maybe there is a definition of the theory that only can be defined on a certain curvature, and simultaneously that curvature is a cutoff of your theory. Now, but you see, we're going towards some disaster slowly, right? Relaxing one, but no, I cannot exclude this thing, but yeah. But I don't think that even on a reasonably carved background, unless you relax some of these analyticity properties.
And could the two-point function just not be analytical?
No, that could be, yeah, but then they have to say that, and then this means that they have to somehow, you will have a very hard job, by the way, very interesting job. I mean, you should not take this as a critic, because I admire this kind of effort, but I'm saying we should do it by obeying rules of quantum field theory, we cannot just break them like randomly, right? So then, if you relax analytic property, this means that you have to deal with causality. And you have to, it's highly non-trivial to maintain causality in theories in which these functions do not have analytic property. Maybe it's possible, I don't know, but
yes, so maybe just to grab the initial question of whether there is agreement or disagreement. I mean, I definitely agree with the question, but with the fact that we have to answer the question, what are the propagation degrees of freedom and are there any instabilities within an asymptotically safe setting?
right.
And we definitely, I mean, we are aware of the question. I just want to add a sort of word of caution that at the moment, within the truncations that we are looking at, we've taken into account a finite number of terms typically. Answering that question would be misleading because we have to look at the full momentum dependence of the propagator. So we definitely have that question in the back of our minds.
No, you are trying to get away from the point. You cannot get away from it. No, sorry. The statement is about Green's function. Sorry.
I don't want to open a long discussion. I just wanted to get the two positions.
No, but it's not a question of position because you cannot. You are trying to appear as if there is a. So my statement about Green's function is whatever it is. Okay, God given, or somebody can compute it for you. He gave you Green's function. So it's a finite, exact Green's function. Now, the moment you tell me that you can trust it, these theorems of quantum theory apply. These are not my theorems, these are quantum theories. Now, of course you can tell me that you are not sure whether your Green's function is trustable. If that's what you are saying, that you have to compute higher corrections to be trustable, that's fine, but then you should... But what I'm saying is that the moment you have a Green's function which is asymptotically safe, you cannot reconcile with this non-existence of the complex residue. That's all I'm saying.
Unless the theory is defined by a non-local terms.
Non-analytic, yes.
Yes. That's why I asked about the non-local terms, that they cannot be cut off and said that we have only R and lambda.
I understand, but then the seminar should start with this postulate. You should say,
that
now
was
I'm
my
going to change
question.
analytic property of the Green's function.
No.
Let's not go into discussion. Just make it clear.
Just a brief comment. So, I think at the end the resolution will be that the renormalized propagator is just p squared, and then it obeys all the Chern-Lehmann theorems that you want to see.
Yeah, but then you are not having anything asymptotically safe. Then it's just under gravity.
Asymptotic safety reflects a unique property of this theory. When you flow away from this point to the infrared point, and from this propagator you should read off your degrees of freedom.
No.
What do you learn from
Yes.
I had a question for Roger and Rose, because I was shocked by Ed's talk, because I'm not an expert on general relativity, but I came away wondering...
Is this on a different topic? A new topic?
Yeah.
So let's close this topic. And,
okay.
No, because I think that I would register that there is a disagreement. So let's close this topic. Yes, please. Go ahead. Sorry. Yeah, go ahead.
Oh, Brian,
Yeah,
so,
I'm not sure. Roger.
this was for Roger, and I really enjoyed Ed's talk, and I came away wondering whether or not general relativity is a consistent theory of space-time, in the sense that we can make predictions, that we can predict about the outcome. Because I was shocked to find out that if I have a spinning star and it collapses, we don't know what its end state is. And then I was even more shocked when Ed said, well, maybe there are echoes when two black holes coalesce.
I don't think that was general relativity. The echoes were something else.
So
Somebody else. I mean, the fact that
well,
we
the
don't
echoes
see echoes
would be due to quantum effects that somehow got up to very big scales.
General relativity says we don't get echoes.
But is general relativity a self-consistent classical theory of space-time?
It's more self-consistent than quantum mechanics.
Let me come in here, because this is, in fact, very close to the third point that I wanted to go to. So I'm formulating a way that joins your question. A lot of people talked about quantum reality. Astley, Francesca gave this quantum model of bouncing black hole, and then also Roberto. Somehow, it seems to me, generativity is perfectly consistent by itself. And it gives a lot of predictions. But generativity, of course, predicts singularities. And a common point of view among many people who work with quantum reality is that when generativity predicts singularity, what is actually happening is that you're leaving the domain of validity of the classical theory, and in one way or the other, quantum theory comes in. I wouldn't say that everybody thinks like that, but this is which would be an answer to your question. But somehow, I trust relativity until quantum mechanics come in, and what happens.
I didn't even want to bring quantum mechanics in. I was just a spinning star. Is the theory, can it predict the evolution of space-time?
So the answer is that generativity.
Even with the singularities. The singularities don't.
Singularity is the end of
I was going to say the singularities that we know, I mean, the ones in black holes and so on, are all in their future type singularities. So, and also well, according to cosmic censorship, it's correct, they don't have any effect. So you don't need to know. And there's a different issue for the Big Bang. That's a different question. But the singularities that we have in black holes, that the theory predicts would happen in black holes, have no. You don't need a theory for them to be able to get predictions.
And do you think you can measure, in assuming classical generativity, everything you can measure, it's predictable, up to the point in which you fall into singularity and die, and or the theory doesn't tell you what happened to the observer that gets to the singularity. If an observer stays outside, it doesn't get signals from the singularity.
Assuming agrees with that.
Prediction.
You agree with that?
Gerhard has a peculiar point of view on that, so I would like to hear Gerhard also.
I think you don't need to know this because it's in the infinite future. Right? So that it is beyond the future of any observer who's staying outside. So if you do physics of our world outside the holes, you never need to know what happens in the singularity. So it could be just a question which has no obvious answer at all. And maybe it's not continuous. You have a differentiation theory where what happens at the singularity is different. And it doesn't matter because of cosmic censorship. This assuming cosmic censorship to work in all circumstances. I personally think it does.
The question remains because quantum mechanics in some way presumably can happen. So the actual question I wanted to ask is where do we expect quantum mechanics can stay? Because that's where we heard of different points of view. And we heard at least three different possibilities. One, which quantum mechanics come in when the curvature is strong at the singularity, well, let's say before or at the singularity. One, which was repeated by various people, is that, and maybe Vali, you're talking about that tomorrow, so maybe I'm thinking too much. Quantum mechanics. Oh, you're not. Okay. Quantum mechanics could have effects outside the horizon as well, and even that quantum mechanics could be relevant and could change the physics entirely. Also in some crossing the horizon and going in. So these are very different points of view, and I see Renata and Francesca.
Yeah, I think so. There is usually so this question is usually repeated. Where are the quantum effects? But one of the things that we are understanding in this model of bouncing black hole is that this is not the good question. Because what you want the question you want to answer is instead, when are the quantum effects? So, also these effects out of the horizon, if you have enough time, they can accumulate and be present there. So it's a bit the same as for atoms. If you wait long enough, a system that seems stable can decay and show a radioactive behavior, show a quantum behavior. So, yeah, so I think that somehow we should keep this in the back of our mind. So when we ask these questions, it's where and when.
Yeah.
Yeah, I have a comment. I was recently at the talk of Yu Unruh and from Pretorius, how exactly this comparison of numerical simulation of the black hole merger, the most violent part, was compared with what actually they have seen in detection, was a quite perfect agreement. And Bill Wonder was insisting that it was many years ago when they were confused how to do numerical simulation when you have singularity. And he just suggested to make an excision. So all numerical data are obtained by ignoring singularity or carefully cutting it out. And the exact precision is quite impressive. So at least we have now a recent information which I think enforces us to rethink under what conditions our knowledge or not knowledge about what exactly happens under the horizon is relevant to anything we can measure in principle.
No, but let me make a comment. An horizon can be very large. Right? In principle, we can have a horizon in which we are. And we may have a certain amount of time toward the singularity crossing the horizon. We could have years. So why shouldn't physics tell us what happens? This is also an objection to how here to what you say. But also not necessarily neither small nor interrupting.
The black hole discuss relatively small from the entire universe. One also said the universe is something else. There, the singularity is different than the Big Bang, the singularity. And you have the horizon of
a very large black hole.
On a large scale.
Say a medium mass black hole. I cross the horizon. Why physics shouldn't tell me what I see a minute later? Would your answer be physics should not answer anything?
No, I think it depends who you are in a sense. You can describe identical situations in different ways. Like in gauge theory, you can choose a different gauge than a different answer. So those answers what gauge you have. So that includes what. So I'll explain that in my talk.
Can I say something? I mean, so let's consider big classical black holes. Right? I will not talk about small ones. So, I mean, we normally believe that these big classical black holes, they're macroscopic classical systems. Right? So, now, if we think about big quantum systems, because at the end of the day, of course, we believe that nature is quantum and black holes are not any different. They are some kind of mean-field description of some underlying quantum state, because they also have entropy and this kind of stuff. Now, then we can ask this question, I mean, for big macroscopic quantum systems that behave classically, when and at what scales are the quantum effects important? And typically the answer is quantum effects are important either at very short scales, in very short wavelength quanta, or at very long time scales. And by the way,
what Francesco was saying.
No, this is absolutely right. By the way, we have seen this explicitly on some toy models. For example, you can take toy model of full quantum gravitational toy model on long scales that we trust, the same techniques that we use for computing density perturbations, etc., etc. We all trust that, right? That's quantum gravity. You can take a toy model of even of the scissor type universe, some toy model, and you can see when this toy model, when the quantum effects are important. We call it quantum break time. I mean, any classical system has a quantum break time. And the quantum break time for a black hole is approximately Page's time.
Okay. I suggest that a simple the discussion, some people are very excited about, other people are very tired. So I propose to close it now. We have 2 more discussions tomorrow evening and the last day. Thank you.